Hey, so the homework that was due this morning at 9, I extended that till 5 p.m. tonight, both the written and the online. So you have till 5 to finish that up. My hope was as many of you as possible would get that done before today's class because it's just really helpful for, this is all building, everything's building on what we did before. So hopefully a good chunk of you got it done. And that's going to be helpful in class. But if not, then you still have till 5 p.m. today. All right. So I want to take us back to the spring example that we never finished. So it's this question. It takes 50 joules of work to stretch a spring 0.08 past its natural length. So if I was talking about the work to stretch a spring, say from 0 to 0.08, what would the structure of that be? What would the structure of that be? Figuring out what the work, the accomplished work is to stretch a spring. Is that just force times distance? Just F times D? So, is that what that is? Because when you stretch a spring, you just apply a force, and you just apply that force and stretch it out over that distance, right? Now, what was the big deal about springs that I jumped up and down about? Force changes. The further you stretch it, the force constantly increases. It takes more force as the string gets longer, or compressing, same way. Okay, so because of that, because the force is continually changing, I can't just write force times distance. How would I have to write the work? How would I have to what's the structure of the work? The force is constantly changing. Little bits of work at a time, right? I'd have to assume a constant force for a little bit of change of distance. But then as soon as you go a little further, it's another amount of work. So I've got to what? I got to add up little bits of work in order to do this. How do I do that? How do I write that? Integral, right? Integral, right? I got to integrate from 0 to 0.08. And then what will go here? If I have the quantity of work that then what goes here? Yeah. Rate of change. What? Rate of change of work, right? So it's rate of change of work. And what is rate of change of work? That's what you said. Force, right? Rate of change of work is force. We saw that with the pushy ant. We saw that with the springs. Rate of change of work is force. So it'd be force. And what is the force to stretch a spring? T, in this case, meters. K times T, right? So the rate of change of work is force. Force to stretch a spring, T meters, is KT. And it tells us that's 50 joules. So we got to this last time, or when we, a couple classes ago. We said that the work, 50 joules to stretch a spring, well, you have to have an integral. You have to have accumulation because that force is continually changing. And you can only do it by adding up bits of work at a time because the force is different for every bit of work. Adding up bits of work, right? Rate of change of work is force. Okay, and so, but then we got here and we said, uh-oh, what happened? We got stuck. Why did we get stuck? We're trying to figure out, this is going to help us find K. And we can't solve for K because in open form, right? This is an open form, which doesn't lend itself to computing easily or doing algebra. Okay? So trying to get this K, but it's locked up in this open form. But now, that's no problem for us, right? So we said, how do we get closed form? Two things that get us closed form. The fundamental theorem of calculus and antiderivative, right? So, KT. We need the antiderivative of kt. What function's derivative gives us k times t? Kt squared. Agree with that? So the great thing about doing antiderivatives is give it a shot, and then what can you do to see if it's right or not? Take the derivative. That's our big theme, right? We're thinking about what function's derivative would give me that. Okay, we'll take a stab and then take the derivative. Is the derivative of this? Has an extra what? 2, right? It gives me 2 kt. We only have kt. So how do I adjust this? Divide by 2, or 1/2. This is kind of reverse power rule, right? Reverse power rule for derivatives would mean raise the power by 1. But then we got to clean up the mess, right? So you can't just raise it by 1 to make 2, because then now it's not, the derivative is now 2 kt. But we just have kt, so we need a 1/2. All right, and then that would be from 0 to 0.08. And we know how to handle that, right? So 50 equals 1/2 k times 0.08 squared minus 1/2 k times. And look, now we've got something easy to solve for k. All right, so motivating closed form, right? So this is a good motivation for having closed form. We can solve this problem, right? We can get k, which is going to be 100. So 2 times 50 is 100 divided by 0.08 squared. This goes to 0. So when this lower limit of integration is 0, does it mean this is always 0 over here? Okay, that's a huge theme today. Huge theme today. Just because you're plugging in 0 doesn't mean this is always 0. Sometimes, yes. Not always. You always have to plug it in. We'll be revisiting that today. So now our k is going to be 2 times 50 over 0.08 squared equals k. And now that I have k, this is a breeze, right? So now I can answer the second question. Now that I have k, applying again. Well, so not only that, I don't have to, now when I do this problem, I don't have to go back and set up open form again. Look, because what do I have right here? I have the closed form net accumulation for work done by the spring, or work that you have to do to stretch the spring. So this is equal to this. Okay, so I just wanted to show you that closed form unlocks this problem for us so we can solve for k and then answer any question we want about the spring. Any questions? Any questions about that? Okay, another example, really important example here. Can I erase? Are we good? This one. Okay, so a culture bacteria in a particular dish has an initial population of 250 cells and grows. And grows at a rate of 50 e to the 0.3 t cells per day. So I want you to write two expressions for p, a function p, the population t days after the initial measurement. I want you to write it in open form and in fully simplified closed form. I'm going to give you 5 minutes to work on this. So go. So you're either making progress or you're getting help, but you're not staring at the screen. Okay? So today's quiz and lecture is actually 3 questions, so it's 3 points. It has to do with this example right here. So brain on, 100% brain on, working hard, listening, getting it, okay, getting it. Go. Good. Okay. All right, lots of people getting this. Good. Okay. I need to change this to the two argument. My slide doesn't have the two argument form. Okay, so this would be one way to write the open form for the total accumulation. So lots of people got it. The only thing I saw was a few people didn't have the plus 250, right? So what kind of function is just the integral? Net accumulation, right? If that's just the amount of change since 0. But if we want total population, we got to add all the population up to 0, right? Or the population at 0, 250. Questions on the open form? Okay, so now how do I want to get an enclosed form. What does that entail? What does it entail? Fundamental theorem of calculus and antiderivative. So we got 50 times e to the 0.3u. This is a slightly harder antiderivative. It's actually like undoing the chain rule because I got this little teeny chain rule in here, 0.3u. So what is the antiderivative of e to the something? E to the same something, right? E to the same something, and then we got to clean up the mess. If we took the derivative of this, we'd have a times 0.3. So the antiderivative needs a divide by 0.3. Right? Because the derivative of e to the 0.3 will be e to the 0.3 times 0.3. A times 0.3 that we don't have here. So we need to divide by 0.3 to take care of that little chain rule in the derivative. Does that make sense? Okay, and so then that's evaluated from 0 to t. We still have the plus 250. Okay, but since I'm plugging in 0, I don't have to worry about that, right? All I have to do is plug in t and add that to 250, right? So this is what the quiz is about today, and what I'm about to talk about, what we're about to do, is on the exam, and we have, from semester to semester, about a 5 to 20% success on this question on the exam. So I'm going to do my best to get that up to maybe 30% this semester. Okay? So yes, we're going to plug in the t, fundamental theorem, plug in the t, plug in the 0, and subtract, right? So I plugged in the t, and I plugged in the 0, and I subtract. So notice, is this 0? E to the 0 is 1. So I have this minus 50 over 0.3. That's part of my total accumulation function in closed form. But that's just a constant. This is like the plus c, right? This is the plus c, or the minus f of a. But because there's also the starting amount 250, in the closed form, I can just combine those together, right? And so when you do 250 minus 50 over 0.3, you get 83.3. So my open form and my closed form. So notice, here's the big takeaway from having to plug in this 0. The constant in closed form, is it the amount of the accumulation at 0? Is it the little f of a? Right? So what I'm asking is this constant right here, is that the same as this constant? No, right? So the amount of population at 0 is the 250, but in closed form, in this case, you don't end up with plus 250. Because when t equals 0, this is not 0. So when you plug 0 in, and add it to 83.3, what will you get? That's the 250, or the population at time 0. Do you see that? When you plug 0, so P of 0 will be the 250, the starting amount. But that happens by this being 100 and something when t equals 0 plus the 83.3 gives you the 250. So the big takeaway is the constant in closed form isn't necessarily the same as this starting amount. Is this making sense? You have to plug the 0 in, and if you want to, when you simplify it, you get a new constant in closed form. That constant is not the starting amount, like the 250 is the starting amount. So let me show you. In open form, what is P of 0? In open form, what's P of 0? 250. It's the starting population. In closed form, what's P of 0? It would be 166.7 e to the 0 plus 83.3, which equals 250. P of 0 is 250. But that's not the constant in closed form. It's on the test. It's on this principle is on the test. You have to plug the 0 in, and you have to combine your constants to get the constant in closed form in simplified form. It's not the 250. Do you see it? Doesn't make sense. Watch for it on the exam. Get it right. Be one of the lucky ones or the smart ones. Yeah.
Could you factor it out so like you can have plus 250 at the end stuff?
Yeah, but so you could have you say plus 166. Wait. Plus 250 minus 166.7. That's how you have to do it. That's what the 83.3 is. So you just wouldn't write that, right? You always would simplify as much as you can. Okay, anybody have a question on this? All right, let's finish out the problem and then we'll take the quiz. What is it doing that? There we go. All right, so I want you to represent in 3 different ways. 3 different ways. Represent the population 10 days after the initial measurement. So in 3 different ways. There's 3 ways you could write out something that would represent or express the population 10 days after the initial measurement. And then find the population, the actual value. So actually there's 4 ways to do it. 3 expressions and a value that all represent the population 10 days, at 10 days. Go. Population at 10 days. So again, I like the two argument notation I should have there instead. Okay, who can give me one way to express the population at 10 days? Who can give me one way? Yes, sir, in the back.
P of 0, 10.
He wants P of 0, 10. Does that do it? That's good. All right. Equals, what's another way to express the population at 10 days? Sarah?
The integral from 0 to 10 of the rate of change of t times dx.
Does that get us the population at 10 days? Almost.
Plus 250.
Right, you got to have the 250 in there. That's right. So what you said was the change in population from day 0 to day 10. You got to add the initial 250. All right, another way to express it. Someone in the back. On this side. Oh, is there a hand somewhere over there? Yeah, please. Okay. How about this? In closed form, express it in closed form. So we got function notation, we can express it in open form, and we can express it in closed form. Doesn't make sense. According to closed form, what's the population at time equals 0? 83.3? 250. According to closed form, it's still 250 when you plug t equals 0 in, because it's the same function. This is the exact same function. They both give 250 as the initial population, even though this constant is plus 83.3. All right, and so then you find which one of these without GC would we use to find the value? The last one, right? Closed form. Allows for computing, right? Allows for computing the value. So we still need a calculator, right? So we still need GC just as an arithmetic calculator. Fine, but what we don't need GC for now is to evaluate open form for us, right? We can just plug that into GC just as it is, and it cranks it out with an easy arithmetic. Anyone got the number? What is it?
313.618.
313. So is it 313? It's at 0.6. So it'll be 313, 313.6, or 314? It'd actually be 313 because you haven't gotten the 14th yet. So you can't have a part of a bacteria, and you haven't gotten to the 14th yet. Even though it's 0.6, you haven't gotten to that next bacteria yet. So at this time, it's still 313. So you don't round in this case. You're just going to truncate off. Does that make sense? Because by 10 days, you haven't really gotten to the 314th bacteria yet. Okay, questions for the quiz? Anybody? Last chance. Here we go. Okay, undoing the product rule. Undoing the product rule. So what is the product rule? It says when you have the product of two functions, the derivative is not the derivative of the first times the derivative of the second, though it's been tried by thousands of calculus students over the ages. It's this instead. It's the first times the derivative of the second plus the second times the derivative of the first. And you might have proved that in Calc 1. You might have showed where that came from in Calc 1. Okay? So if we took the antiderivative of both sides here, that would look like this, right? The antiderivative of the left would just be the FG. And then on the right side, we'd have antiderivative of FG prime dx and the antiderivative of GF prime dx. Okay, so undoing the product rule, it's a little bit different than here's the result. You get this sum of two things, and then you have to come up with the f times g. Instead, your given integral is like one of the terms of the product rule. So we want to get this net accumulation function in closed form, or this antiderivative. But this, whatever we have here, it's a product, but it's not. For instance, it can't be done by undoing the chain rule. So what happens is we consider it as one of the terms of the product rule, and when we figure out what the other term of the product rule is, it turns out that is an attainable antiderivative. That one's easier. That one we can kind of do more on the spot. So by figuring out what the other term of the product rule would be and seeing that it's attainable, then that gives us a way to get this. So what would it be? What would this now equal? How would we solve for this given problem? What would we have to do? just one step of algebra, which would be, what does this equal in this equation? Just think algebra. C equals A plus B. So how do you solve for A? C minus B. Right? If I can get this antiderivative, and I know what f and g are, then I can just do fg minus this one, and that equals the one that I want. So here's the overall strategy. We're going to think of the fg prime as one of the terms in the product rule. We're going to determine f and g. Then we're going to compute f and g, and we're going to set up this antiderivative. And if we've done everything right, that will be easier. And then we're going to solve for this indirectly by doing fg minus the green one. So it's kind of like an indirect, it's kind of like a workaround, right? It's like a workaround to do this by finding other stuff, right? But all that other stuff is based on the product rule. So does the overall approach make sense? Okay, let's try an example. So that's what I just had written. Okay? So let's try integral of 4x cosine x. So we're going to start learning several techniques, okay? And so then by the end, there's going to be this important skill of you just come to any integral, any net accumulation function, you got to figure out which technique to use. So here's kind of a roadmap. The first question would be just, is it just easy? Is it just a rule? Easy rule. You know, like if you have the integral of secant squared, what is that? What's the antiderivative of secant squared? Tangent, right? So it's just a rule you've memorized. There's no technique. It's just the rule. The second, if it's not one of those, the second go-to is undoing chain. That will always be this is the most prevalent technique. And so it's kind of a go-to, like in terms of harder ones. It's always the one you ask first. So we're going to come to this and say, is it undoing the chain rule? And in order for it to be undoing the chain rule, we talked about last time, it has to meet that requirement. What's that requirement for undoing the chain rule? This relationship right here. That one of your factors is the derivative of the interior of the other. That means it came from the chain rule. So, is one of these factors the derivative of the interior of the other? No. So now we're gonna, as an aside here, we're gonna say, what small change would have to be made to this so that it would be undoing the chain rule? So like, what different problem that's really close to that, what different problem would be undoing the chain rule? So, and then we're gonna ask this question a lot because it's really good for identifying undoing the chain rule. So what small change could I make here, say in red, so that would then be undoing the chain rule? What's that? She's suggesting cosine of x squared. If it was cosine of x squared, now would it be undoing the chain rule? So now do we have a derivative of an interior function? What's the derivative then? Yeah, so right here, this is essentially, it's off by a factor. That's no problem though. The constant multiples are no problem. This is now essentially the derivative of x squared. So she got it. Does that make sense? If it were 4x cosine x squared, we would be doing undoing the chain rule because it meets the requirement of that is essentially the derivative of the interior, and we could do that. Okay, but that's not our problem. Our problem is this one. So we've got a product of two things. Maybe it is undoing the product rule, right? So maybe it's gf prime. So then the question is, what is the g and what is the f prime? Well, when we're first starting out, we don't have much experience, so we just make a guess. Just go for it. And then work out what the other integral was, right? The integral of fg prime. And if that other integral is easier, then it worked. So let's just go with g is 4x and f prime is cosine x and see what happens. So what are we going to need? We're going to need g prime. We're going to need f. So if g is 4x, then g prime is 4. And if f prime is cosine x, then f is, that's like a little, you got a little antiderivative in there. So that's our setup work. And what did we say? We said fg equals integral fg prime. Shoot, did I? All right, so I used the wrong symbols here, sorry. So we wanted this to be fg prime. It doesn't matter, but I want to be consistent with what I told you earlier. So this should have been f and g prime. Sorry. All right, so this is consistent with what we talked about earlier. That fg is fg prime dx plus gf prime dx. So that's the product. That's the antiderivative version of the product rule. And so we said here, this is what we have, fg prime. So let's just call f 4x and g prime cosine x. Then the derivative of f prime is 4. Antiderivative is sine x. So now this is what we're solving for. So I'm just going to call it capital A for, say, answer. Okay? Capital A for answer. That's what we're trying to find. All right, so then we're going to set up this one. So it's going to be the antiderivative of g f prime dx. That would be sine x times 4. And so we can just stop right there and ask the question, is this an easier doable integral for sine x? Certainly, right? That's just goes back to an easy rule. And so then we're on the right track here. So f times g then over here on the left is going to be the 4x sine x. Okay, so then we're home free. A equals what? This minus this, right? We're just solving this big equation for A. So A equals 4x sine x minus integral of 4 sine x which is 4x sine x minus antiderivative of sine x is, what function gives derivative of sine x? Negative cosine. And then remember, this is what? All net accumulation functions, starting from any a, right? So that means we'll have a minus f of a, and we know that's plus c. How can we check to see if it's right? Take the derivative. We want to get to another example, so we're not going to take the derivative of this. But if you're to take the derivative of this, it should be exactly, if you do all the math right, what you started with. And it will be. You've got a little product rule there, minus this here, will end up being that. So notice what happened, right? Why did this work? It's because we chose the 4x to be f, when we took the derivative, its power went down by 1. You see that? And when its power went down by 1, then we ended up with 4x to the 0, or just 4 sine x, which made it a doable antiderivative. So that's now that we have a little experience, we can see, okay, so maybe that's a good thing. If you've got like a power of x times some other function, maybe that's what we want to assign to f. That worked here. Any questions on that? Okay, another example. X squared e to the 3x. Okay, so is it undoing the chain rule? Or product rule, not chain. Is it undoing the chain rule? X squared e to the 3x. What small change would make it undoing the chain rule? How could I make a tiny change to this so it would be undoing the chain rule? 3x. I heard squared and cubed. Cubed. Why? Because this has to be essentially the derivative of this interior function. So we need power 3 here. I need power 3 here to match up power 2 there. So only power 3 here with x squared would make this undoing the chain rule. That's not what we have. So we have a product, so maybe we'll try undoing the product rule here. So we got to assign our f and our g prime. So we saw this work last time, so let's try this now to make the f the x term. All right, what's the antiderivative of e to the 3x? E to the 3x, right? Anything else? So we think about taking the derivative of this. If we take the derivative, we'll also have a, by the chain rule, we'll have a 3, which we don't have here. So we need over 3. Okay, so we're going to set it up. So we're going to have fg equals our answer plus integral gf prime. And so we got what? X squared times 1/3 e to the 3x equals our answer plus integral of g f prime, or I'm just going to change the order, f prime g, 2x times 1/3 e to the 3x. So we come to this one, and we say, is it easier? Is it doable? You good? All right, so is it easier? Is it doable? Well, no, it's kind of like we have the same situation again, right? I got an x times e to the 3x. So what now? So yeah, it's kind of simpler because instead of x squared, I have x. But still, I got this problem. I got x times e to the 3x, and it's not undoing the chain rule. Okay, so do you recognize that? We could take this one, and we can do it again as a problem within a problem, right? So I could come over here. And I can do this same technique on this one. So what would we do? So I'm going to use capitals over here. So f and say g prime. And make my f 2x and my g prime 1/3 e to the 3x. Which would make f prime equal to 2. And now g would be, we need another factor of 1/3. And so now in this little subproblem, I'll have fg equals my answer to this, I'll call it a star, plus integral of 2 times 1/9 e to the 3x Is that easier? Can we do that? Yes. That one we can do. And so then in this subproblem, we'll solve for a star. And once we get a star will be something. That will be this. And then we can solve for our original problem, which is a. A will be this minus the solution we get in the green box. But we're out of time.